Okay, so Margaret, do we see the title slide?
Yep, we can see the title slide.
Okay, great. So thanks everybody. What a fantastic day to be doing lunar science on the anniversary of the Apollo 11 landing. I still remember being an annoying young teenager in my sister's bedroom watching Neil step out on the moon, and now here we are still doing amazing lunar science. So today I'm going to be reporting on a paper by Casey Honniball. Casey's on maternity leave. Sort of ironically, we're reporting on the Sophia Observatory, which is about to go on eternity leave. But the observatory still has some lunar science to do, and I'll be talking about that at the end. So first of all, we try to understand the lunar volatile system in terms of models, and Brant Jones is going to show a great example later in the session. We can break this down into a framework of sources. Where does water and its precursors come into the lunar environment? Processes, how does the lunar environment alter the precursor materials? How about transport? How does water actually move through the lunar environment? There's sequestration. There are numerous sinks for water on the moon, and what are the efficiencies that they retain water? And finally, loss. How is water removed from the lunar environment, and from what sinks and at what rates? And despite the fact we try to understand all of this in terms of models, the answers depend on measurements. And what I'll be talking about today is an aspect of what hydrogen-bearing phases are present in what reservoirs and what are their amounts and behaviors. And many of the talks will be on the same topic. So first, we'll be reporting results from the Stratospheric Observatory for Infrared Astronomy. So this is a 2.5 meter infrared telescope mounted in a 747, flies above the majority of water in the atmosphere, which opens up the window between 5 and 8 microns, which is closed to ground-based observatories. We use a spectrometer called Forecast that operates from 5 to 8 microns. We have more or less 2 to 4 kilometer resolution at the center of disk. Foreshortening reduces that towards the limb. And what we're doing here is we're measuring a unique spectral feature that the water molecule exhibits on the surface, which is a fundamental emission feature due to the HOH bend. The unique contribution comes from the fact that only HOH has the spectral features. OH connected to other cations do not have this feature at 6 microns. So unlike at 3 microns, where there's sort of persistent ambiguity between OH bonded to various cations and H2O, at 6 microns, we're uniquely sensitive to the water molecule. Sophia is also unique that we can't see this from the ground, but also currently there are no planned missions that include this 6 micron observation, but hopefully our work has put a twinkle in instrument and mission proposers to make this measurement from lunar orbit in the future. So in 2020, we first detected this 6 micron emission feature on the sunlit lunar surface. The plot in the upper right shows the emission band. It shows that the water molecule itself is present outside permanent shadow. Ice had been detected by UV and near infrared methods, Hain et al. and Lee et al. And in this, the data we showed, the abundances were on the order of 100 to 400 ppm H2O. Now in this work, we collected data again at high southern latitudes, but adjacent to our previous measurements. So we took 94 frames of data. This is an imaging spectrometer, more or less like M-Cube with a long slit spectrometer. and 32 reference frames. I should point out that all of our data are differential. There are technical aspects of forecasts that mean that we have to ratio all of our data to a reference, and we typically try to have a Mare reference that's near the subsolar point and in the equator, with the expectation, but not a requirement, that that Mare reference will have less water. And we published this paper recently in GRL. So actually mapping the data on the surface, our team member, Eric Malloret, Applied Coherent Technologies, the famous developer of QuickMap, has been putting the data into the lunar cartographic system. And so what you see on the right are how the slits actually map on data in polar projection. In the upper, on the image on the left, you can see our reference locations, and then on the bottom is the distribution of points in the target location. This was actually a training flight to develop the mapping procedures. All of the data we've taken subsequently have nice tight maps, but you'll see some decent examples of how well we're doing in the mapping. And you can see in this particular data set, we've collected data near the Viper landing site and have done much better subsequently. So here's those data in orthographic projection, and you can see the spectral, the crater features and other features on this plot. At 6 microns, we're all entirely in thermal emission. And so the brightness we see is controlled by the incidence angle of the sun. So when you're near a terminator situation, you see craters and whatnot. This is typical for thermal infrared observations at low sun angles. Again, we developed all the techniques for doing our mapping situation. So here's some results of the 6 micron band. So this is the 6 micron band enjoying a zoom call in Brady Bunch mode. So Casey fit all of these spectra with Gaussian fits, so we could examine its relationship to other water-bearing materials that exhibit 6 micron data. And in this particular set of data, all of the data at the high southern latitudes exhibited a 6 micron band. So in the left, this plot in the red shows the distribution of the center of the 6 micron feature that we observed versus the width in microns, and that's for the current data. The gray points in the background are 2018 data, so those overlap. And I'll just draw your attention to the black squares are meteorites that have adsorbed terrestrial water and how their centers and widths plot. And then in a blue circle is a Morb glass that Choi Lee dehydrated in his thesis, and his data show how that 6 micron feature behaves with the dehydration. We have very good statistical significance for almost all the data, and the H2O contents vary from about 200 to 350 ppm water. And again, this is a lower limit. If there's some water at that reference site, then that will be added to this lower limit. So here's a map of both flux and water near the region. So as I said, we can see this Mauritius crater map. This is partly interpolated map. And in the right, you can see the water map, which shows a correlation with latitude and an inverse correlation with flux. In subsequent data sets, we're starting to see local anomalies as are observed at 3 microns. Apologies for this long slide, but this is when we published our data in 2020 on the 2018 data, working with Michael Poston, the residence time on the surface is so short that we basically dismissed the possibility of water on that the water was actually exchangeable, or that it must have been trapped in glasses or potentially in very tortuous paths through between grains on its way out of the surface. We've done some subsequent calculations I won't go through here, but basically we estimate the potential exchangeable water from our ppm measurement, assume we've got a few grains deep of exchangeable optical surface, and then we compare the residence time at our temperatures, which were about 300 K, to the flight time of molecules through the surface. And when you do the math, you get very high abundances of exospheric water, which either means that the Lati upper limit is only relevant to the equator, or the water is not exchangeable, and we're hitching our wagon to the water being trapped and not exchangeable.
Paul, we're out of time. Could you leave up your conclusions while we move to the next speaker, please?
Okay.
Thanks so much.
Sure. Go ahead.
So please give Paul a round of applause while we get the next speaker's talk up.